We're going to turn now to a treatment of the Doppler effect for sound. Now, when the source and or observer are not at rest with respect to each other, the frequency of sound as measured by the observer changes. In this example, we have a source moving towards the observer at some speed, which is subsonic, so less than the speed of sound. This causes an increase in the frequency as measured by the observer. Of course, if the observer were over here with the source moving away, then we'd see a decrease in the frequency. So the source moves toward the observer, the wavelength goes down, frequency goes up. We'll define the velocity of the source Vs to be positive when it's moving towards the observer, and do a derivation to see what the change in frequency is. So here again is the moving source. We see compression of the wavefronts, and our task now is to calculate this new wavelength, and therefore the new frequency. So at rest, we're going to have the source with a period of t, which is equal to 1 on f. Now, with wavelength lambda, we have c equals lambda f, which is equivalent to lambda is equal to t times c, the period times the speed of sound. When the source moves at velocity vs towards the observer, the space between successive wavefronts, lambda dashed, so this is the wavelength as seen by the observer, is given by the previous wavelength, and we subtract off t times vs. So this is the distance that the source travels in that period t, and so this gives us the compressed wavelength. Using t is 1 on f, we get lambda dashed as equal to the difference in velocities divided by the frequency. The wave velocity is unchanged, so if you ask the observer here what the speed of sound is, they tell you the same speed of sound as the source. So we can write f dashed is equal to c on lambda dashed, or in other words, f dashed is the frequency multiplied by this factor here. So this is the new frequency, and we can see that if Vs is positive, then we have a number here which is less than c, causing an increase in frequency. What about a moving observer? So we're thinking about this situation now. We've got an observer moving away from the source. And we're going to have the same setup here, that the source has period 1 on f and c equals lambda f. And when the observer moves at velocity v0 away from the source, we find an observed period. So we're calculating now the observed period. The observed period is the distance between the wave fronts, which is lambda, divided by the difference in velocities between c, the speed of the sound, and v0, the speed of the observer. So this is the new period, and we can rearrange that to find, in terms of the frequency, and therefore find the new frequency as 1 on t dashed is equal to f on c multiplied by c minus v0. And we can see now as well, if v0 is positive, then we have a number up here which is less than c, giving us a reduction in frequency as we want. We can combine these two results so that if we have now a moving source and a moving observer, then we have a new frequency given by this equation here. So we have moving observer and moving source. Now in this animation, Vs is positive, which increases the frequency at the observer, and Vo is negative, again increasing the frequency at the observer. So moving towards each other. So both these factors, top and bottom, cause an increase in the frequency. One special case would be this one here, where we have the source and the observer moving in the same speed in the same direction. In this case, the two factors cancel out, and the original frequency is the same as the Doppler shifted frequency. Now this is all true for when the speeds are less than the speed of sound. If we go to a case where the source is now moving at the speed of sound, then we have a situation like this. So now the source is moving along the same as the wave speed, and so all these waves here are compacting and adding up with each other. And this is what a sonic boom is. It means all of these wavefronts here are constructively interfering with each other, and you're getting a really, really big sound wave at this shock front here, which forms a shock wave, in fact. If the speed is now much larger than the speed of sound, we also get a shock wave, but now the shock wave has some angle. So a shock wave here is just a really, really big sound intensity caused by constructive interference of all these sound waves. And in fact, it can become quite non-linear and can't be described so well with simple linear wave mechanics. You can see this sort of effect as well on water. So here's a boat and a duck, both generating a bow wave. And boat speed, and indeed duck speed, are generally greater than the speed of water waves. And so you see the same kind of angle here, which is comes about due to the supersonic motion of the wave source. It's a little bit more complicated in water because of dispersion. The speed of different waves, depending on their frequency, is different in water. And if you want to know more, then I recommend this source. It's a journal article explaining how you calculate the angle of these bow waves in water.